Okay, quickly. So this problem for your Wednesday's homework was flawed. It's not really. It doesn't work. So I went to the author and who's actually he's gonna guest lecture after spring break, and his intention was that this would be the rate function. But this is if you're trying to get an accumulation of weight function, weight is force. This is the force between two objects. So this would not be the rate. This would be the weight itself. Okay, this would not be the rate of change of weight, but this would be weight because it's the force between the two objects. So because of that, the problem is flawed. But as a consolation, if you worked at it and made some progress, you thought about some correct principles, it's not all for naught. So, but it's not going to give you the way this is set up. It's not going to give you a credible answer. Okay, so just wanted to let you know that. Okay, our next exam is a week from today. That's Friday before spring break. So I'm going to post some study resources today. If you didn't do as well as you hoped on the first exam, that means you need to get started studying early. Don't wait till Wednesday. Certainly not Thursday. You're going to start studying this weekend or early next week, and then you got to figure out what it is you really do know and what you don't, and then get your questions answered. Find us, TAs or myself, and work out the things you don't understand. Okay? All right. Yep, same procedure and room as last time. So what was that? That was the art building, second floor or something? 220? Thank you. Art 220, same procedure as last time. Yeah?
This exam is going to be word problems and methods of integration.
Yeah, so it's going to be where we did volume. So it's actually going to overlap a little bit. There's area and volume is going to be fair game. And then we have arc length and surface area. And then we have the physics, and then we have the integration techniques. Yep. All that. Other questions? Okay, so let's do our next technique. So I looked at the results of the undoing the product rule on WebWork, and there was high success on all the problems, so we'll just keep moving on. Just know that as you continue to get more WebWork, any technique that we've learned so far is fair game. Okay, and that's what you got to learn to do. You got to learn to identify first. So yes, we're coming and we're going to do one technique at a time and learn each technique at a time. But then when you come to the exam, you come to an antiderivative and you got to know what to do. So there's this identifying what technique applies skill that you have to have too. You have to have the skill for that too. All right, so the next one is we're going to talk about finding the antiderivative of a rate of change function that is a rational function. What's a rational function? Rational has the word ratio in it. So, has the word ratio in it. So what's a rational function? It's the ratio of polynomials. Ratio of polynomials. That's what a rational function is. So one polynomial divided by another. So the first thing when we have one of these, what's the first thing we always ask? Is it undoing the chain rule? Is it undoing the chain rule? So we look at this, 2x squared over x plus 1. Is it undoing the chain rule? What one small change to this rate of change function would make the undoing the chain rule technique apply? Where? If it was x cubed plus 1 in the denominator, then would it be undoing the chain rule? You should see yes. And what would the first attempt be? Right? We have x cubed plus 1. That's to the first power in the denominator, right? Or to the negative 1 power. So first attempt would be natural log. Absolute value, x cubed plus 1. That might be a first attempt. Okay. Again, if you weren't anticipating that before we were talking about it and I'm writing it down, then you might need to go back and relearn undoing the chain rule. You've got to know that. That's the most important one. And you have to be on look out for it and know it quickly. So that'd be a first attempt if it were x cubed plus 1, but it's not. So it's not undoing the chain rule. The powers don't work out, right? So we've got a rational function. So we think it might be this technique we're about to learn. So here's the first thing we're going to do when you have a rational function. And it's not undoing the chain rule, and it's not really one of the common forms of undoing the product rule. Remember I went over those common forms of undoing the product rule? It's not one of those. So we might hesitate with that as well. So the first thing we're going to look at in a rational function is compare the degree of the numerator and the denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, we're going to start by long dividing. We're going to long divide this. And the way you long divide is the same way you long divide numbers. So we're going to put the divisor over here. And the dividend over here. And we got to leave room for every power. So 2x squared plus how many x's? How many constants? So make sure you have a column for every power of x, even if they're missing. So we don't have a x term, so it's 0x. No constant, so plus 0. And then what our quotient is going to be, what? So we need to get what? In long division, we need to get 2x squared here, so when they subtract away. Remember that from your long division? All right, so what times x gives 2x squared? 2x. And so the 2x, I'm going to put it right above the 0x, because it's then the x to the first column. And so I'm going to multiply that 2x times the divisor, so I get 2x squared plus 2x, and then I'm going to subtract. And the reason we chose 2x was so that we'd have 2x squared, and this would go away and be 0, right? That's why we chose the 2x, so that we get a 0 there in that left-hand column. And then we subtract here. 0x minus 2x is negative 2x. Remember? And then you bring down the next term, so plus 0. And then we say, what do we need to, so now again, we need that minus 2x when we subtract to go away. So what do we need to multiply x by to get minus 2x? Negative 2, that's a constant, so it goes in the constant column. Minus 2 times x plus 1 is negative 2x, that's what we wanted, minus 2. And now we're going to subtract. And we get 2. And that, since there's nothing more to bring down, that's our remainder. So we can rewrite this expression as the quotient plus the remainder over the divisor. Remember all this from your advanced algebra? And so it's going to be, this is going to be the same as 2x minus 2 plus the remainder divided by the divisor. So by long dividing, we get an equivalent expression. So this is another way to write this same rate function. Did I make any algebra mistakes? I will do that. So if you think I made a mistake, algebra, arithmetic, don't hesitate to speak up, because we don't want to dig a hole here. Does everything look good? Okay, and so then the next thing we do is we look at this and we say, can we do it? Can we just do it? Yeah, this is easy now. Antiderivative of 2x is x squared. Antiderivative of 2 is 2x. Antiderivative of 2 over x plus 1. 2 natural log, absolute value, x plus 1. We need all accumulation functions that have that rate function plus c, right? Not just the one that has a f of a of 0. Okay, so that's the first thing you look for in these rational. So first thing you look for is it undoing the chain rule? No, powers aren't right. Okay, is it undoing the product rule? Well, it might work, but it's not one of our common forms, so we might be a little hesitant. Okay, but it might still work if we worked at it. But since it's a rational function, we say, could we long divide? Could we long divide? When can we long divide? If the degree of the numerator is greater than or equal to the degree of the denominator. Long divide, and now we got something we can do. Now, when you do this long division, what you might get is something like this, where n now is less than d. So when n is less than d, we have a new technique that I'm about to show you, okay? And so you might have to apply, in this case we didn't have to, because 2 over x plus 1, we can do that, we can get that accumulation function easily. But if n is less than d and it's still something that's not, readily solvable, then we have another technique that we're about to start now. But when you have a rational function, always look at the degrees first and long divide if n is greater than or equal to d. All right, so now what about if a fraction is n less than d? What about if a fraction is, and you can't just do it easily like this one. Any questions on this first example? Go on to the next one. Here we go. All right, so if n is less than d, so there's 2 qualifications for this technique I'm about to show you. The degree of the numerator has to be less than the degree of the denominator, and the denominator has to be able to be written as a product, meaning it has to be able to factor into at least 2 factors. Okay? Both things must be true for today's technique to work. It's called partial fractions. Okay? For partial fractions to work, you need two requirements. The degree of the numerator is less than the degree of the denominator, and the denominator has to be factorable into at least 2 factors. Does this qualify? First of all, is the degree of the numerator less than the degree of the denominator? Yes. Degree of the numerator is? What I mean by that is, so you have a polynomial, the highest power of exponents, right? The highest power, that's the degree. So what's the degree of the numerator? 1. Degree of the denominator? 2. Okay, so check. Second requirement that needs to be met is, does the denominator factor? Can it break apart into at least 2 things multiplied together? So this is our, back in our algebra days, right? Can we write it like this? Can we get it to work? So we got 2x squared, so 2x and x. And what? We need something that multiplies to -1, but then the middle terms add up to -1 also. Does it work? 2x plus 1 and 2x minus 1. So we got our product of -1. 1 times -1 is -1, and then 1x minus 2x minus x, got it. So, check. So now we can use this thing called partial fractions. The idea of partial fractions is, it's kind of going in reverse of how you add fractions. What's the key thing that you need to be able to add or subtract fractions together? Common denominator. So what we're really doing here is we're saying, look, here is the common denominator resulting from adding or subtracting these. We're going to go backwards and split them apart and get the sum or difference of 2 fractions that would give us that. Does that make sense? So really what we're saying is we want to rewrite this as a some numerator over 2x plus 1 plus some different numerator over x minus 1. Because if you had 2x plus 1 and x minus 1 as your denominators, the common denominator for adding those would be the product of those 2, right? So if we could figure out what numerators make this sum equal to what we had, then we have a new version of the rate function that we can get the antiderivative by doing them one at a time, right? We could do this antiderivative and this antiderivative. Okay, so what are we going to do? So we're going to take this now and do what we would do if we were adding them together. It's just we don't know what the numerators are. We're just going to call them capital A and capital D. Okay, so what if we were to add those together? what would it be? So a over 2x plus 1 plus b over x minus 1 would equal what? So how would we add these together? So what do we need to do to the first fraction to get that common denominator? X minus 1 over x minus 1. Remember doing this? And I'm just going to write common denominator. Okay, CD. What's the common denominator? I'm going to write it out. 2x plus 1, x minus 1. So I multiplied that first fraction by x minus 1 over x minus 1 so that the denominator is right. Same thing with the second one. You're going to multiply that one by 2x plus 1. And then when we add these two together, we're going to have our common denominator. That's the one we started with, right? 2x plus 1 times x minus 1. And we're going to have, in the top, a times x minus 1 plus b times 2x plus 1. So we want this to be equal to the original rate function we were given. The denominators are the same. So what? We need the numerators to be the same. We need 5x plus 1 to be the same as that. We need to find the values of a and b that make this thing equal to 5x plus 1. And then we'll have our a and b, and we can do the antiderivative of this. So we're looking at taking this thing right here and setting it equal to 5x plus 1. And if we can find the value of a and the value of b that make that numerator equal to 5x plus 1, then we're home free. We can rewrite our integral this way. So let's take a look. So I'm going to do, ax, I'm going to multiply out now, minus a plus 2x, or let's see, b times 2x plus b equals 5x plus 1. So what we're going to do is we're going to go through every power of x over here and figure out what the coefficient is. So what's our coefficient? Our coefficient here is 5. Blue triangle around that. And so what has to equal 5? What has to equal 5? All the sums of the coefficients of x on the left. So what has to equal 5? A plus 2b. Right? So all the coefficients of x over here have to sum up to be 5 because of the coefficient of x over here. And then 1. That's our constant. What has to equal 1? Negative, yeah, b minus a, or negative a plus b. So we got a plus 2b equals 5, and minus a plus b equals 1. Now we've got to find a and b. Stop me if I lose you. Any questions? So now we've got what? 2 equations and 2 variables. There are various ways, there are multiple ways to solve that. Take your pick. Take your pick. In this case, so there's what? There's substitution, there's elimination. You could use a little matrix method, whatever works. But in this case, we got an a and a minus a, and this thing is just all set up to add equations, right? This is called elimination. If we add these 2 equations together, then we're going to eliminate a automatically because you got a plus a and a minus a. So we're going to add together. We get 0a, and we get how many b? 3b equals 6. Therefore, b equals 2. And then I can put the b equals 2 into either one of these and get what a is. A is positive 1. So yeah, if you put b in, say, for here, then you have negative a plus b equals 1. So the opposite of 1 plus 2 would be 1. All right, and so then we can rewrite this now. So our original antiderivative is the same as a, which is 1 over 2x plus 1. And I'm just going to go ahead and split it up into 2. 2 over x minus 1. Easy peasy, as my son would say. Natural log of absolute value 2x plus 1. Is it right? Careful. Think about taking the derivative of that. Think about taking the derivative. This is like our undoing the chain rule, right? Take the derivative, you get a 2. A 2 that you don't have here. Therefore, and then plus all accumulation functions that have that original rate function. Did I lose you? Ask if I lost you. So this is all based on common denominator and adding fractions, but it's like we're taking that final result of an addition and pulling it apart into 2 that we can do. All right? Any questions? Another example. Okay, this one. So, is it undoing the chain rule? Oh no, right? Oh no. Okay? Is it undoing the product rule? Wouldn't want to try, right? Wouldn't want to try. Okay? So, do we have a rational function where the numerator is, so how does the degree, what's the degree of the numerator? 2. Degree of the denominator is? 3, because you have x squared, and then that would be times 1x over here, so the degree here is 3. So, is degree of the numerator less than denominator? Yes. Does the denominator factor into at least 2 factors? Yeah, and they started off that way. So it's like they did that work for us already. So if it were just a polynomial as a sum of terms, you'd have to determine how it factors and then factor it. But here it's just given as factored. Okay, so here we're going to write out the different, we're going to write this out as the different possible denominators. Okay, so what possible denominators are going to come into this here? X minus 3 is one. X minus 2 squared is one, but then there's another one. Just plain x minus 2. You have to cover all possible, actually, sorry, I don't want to write these separate. Right. Sorry. All right, so x minus 3. X minus 2 squared. And x minus 2. So we've got to cover all our bases here, all possible parts of our factors of the denominator that could stand alone when we added them together in the first place. So you might say, well, why don't we need one that has x minus 2 times x minus 3 in the denominator? No, because that will be covered by these two added. Okay, so when you add these two together, you're taking care of the factor of x minus 3 times x minus 2. But none of these here, x minus 2 squared, different than x minus 2, different than x minus 3. But then that covers all the bases. Yeah?
Why is there an x minus 2 squared and an x minus 2?
Because we have to cover all the bases. Because, so yes, if we have to allow for all possibilities of our final answer. If you started with this and you were adding fractions, yes, the common denominator would be this. But we're going backwards, so we need to account for all possibilities. And there's a possibility that you could have a fraction with just x minus 2 in the denominator. So you're right. If this was not here and we were adding these fractions, you'd get that common denominator. But it's possible that you can't possibly add two fractions like this and get x squared plus 1 in the numerator.
So we won't necessarily know if we're going to use all of those.
That's right.
At the end.
Yep, so we're going to have A here, and B here, and C here. So we might get one of those three to be 0. We will not get A to be 0, right? So now the only one that might be 0 is C. There's got to be an x minus 3 factor, and there has to be x minus 2 squared. So the only one that might turn out to be 0 is C. But if C isn't 0, then it's a good thing we had it, or else we wouldn't have gotten it. We couldn't have done it. Okay. All right, so here we go. I want you to, so I'm going to take attendance. I want you to work on this now. So this is the algebra now. So what's the next step? The next step is to figure out what you need to do to each of these three so that you would add them together with the common denominator. Then you've got your numerator. Your new numerator is going to be equal to x squared plus 1. You're going to match up the coefficients for like powers, and then you're going to have a system of equations. You've got to solve that system of equations. So work together, get help if you need help. You're either making progress or you're getting help. Go. Check that you have this step. Check that you have this step. This is what we're heading for. What is that? The numerator has to equal x squared plus 1. Is that a question? What's that? We need one more x minus 2. We've got one x minus 2. We need one more x minus 2, and then the x plus 3, or x minus 3. And then we get x minus 2 squared times x minus 3, right? So times x minus 2 times x minus 3. So that's what that last one looks like when you... And that gives us the common denominator of x minus 2 squared, x minus 3. Follow it? And so then on the top we have c times x minus 2, x minus 3. Does that make sense? Nice and loud, nice and loud. No, you already have one. You already have one. So the one you already have with one more gives you the x minus 2 squared. If you put squared here, then that's x minus 2 cubed. Just like over here, or say this one. Did you write any more x minus 2s? Yeah, so you don't need it. So you've got x minus 2 squared. All you need is x minus 3 for this one. You're asking what do you multiply by to achieve the common denominator? And that includes what you already have. Okay, other questions? Are we good? If I make a mistake, please alert me, stop me. Don't let me get to the end of the problem and tell me there's a mistake on this line. I'm going to rewrite this as x squared plus 0x plus 1. X squared terms, blue triangles. X terms, red circles. Constant terms, black squiggles. It's like Lucky Charms, right? All right, so x, our coefficient of x squared is 1. What has to equal 1? A plus c. All right, red is our going to equal to 0. We got minus 4a, make sure, plus b, minus 5c, and then finally constant terms. 4a minus 3b plus 6c equals 1. Agree with this so far? Yes. Have a question? Did I lose you? But I have several people who've gotten the same thing as me? Cool. All right, what now? So now we got 3 variables and 3 equations. Again, any way you want to solve this is fair game. Okay, so I'm going to do it one way, but in the end, we just need to get the values of a, b, and c that make all 3 of these work. Okay, so that means maybe substitution, maybe elimination, a matrix solution, whatever. Okay, so I'm going to look at this and say, if I could eliminate b from these second 2 equations, then I'd have this equation of a and c, this first one, and I'd have a new equation of a and c. And then I could work on a and c as 2 equations, 2 variables. So that's what I'm going to do. So to do that, I'm going to take the second equation, and I'm going to multiply by 3. If I multiply the second equation by 3 and add them together, the b's will go away. Do you see that? Because I'll have positive 3b and minus 3b. So when I do that, I'm going to have negative 12a plus 4a. What's that? I think that's negative 8a. Do you see it? Positive 3b minus 3b is 0. Negative 15c plus 6c. Negative 9c. And then 3 times 0 plus 1. So now I've got a plus c is 1 and minus 8a minus 9c equals 1. And I can combine those. I can combine those 2 equations, 2 variables. So how can I do that? So now I'll just, for variety's sake, let's do substitution now. So I'm going to solve this first equation for a. So a equals 1 minus c. And I'll take the 1 minus c and I'll plug it in for a down here. And then I'll have an equation of c. So then I'll take this and I'll say minus 8 times 1 minus c minus 9c equals 1. So I substituted in 1 minus c for a here, getting that from this one here. Again, this is one of 100 ways to solve this system of equations. If you're doing it a different way, as long as we get the same a, b, and c in the end, that's all that matters. Okay? Any way you want to solve it. All right, so what do we got? It looks like I got minus 9c and plus 8c. Looks like minus 1c. And then I got minus 8 And I'm going to add that to both sides. Positive 9. So I get c equals negative a ninth. Anybody else?
No.
Negative 9. See, good thing you guys are here. Negative 9. I was thinking 9c equals 1. Okay? C equals negative 9. And then we just go back. So then we can easily find A. So all these equations, if we've done it right, are all true statements. Use the easiest ones to achieve your goal. So from c equals negative 9, the easiest way to get A is here, which is 10. And then maybe the easiest way to get B, that is from this red equation, maybe. So B would be, this is negative 40, so add it over here, we got positive 40, and then we got positive 45, added over here is negative 45, so it's negative 5? What did I do? I just plugged A and C into this red equation and solved for B. Okay, so now I have, let's carve out some new room for myself here. So now our original integral is the same as 10 over x minus 3. Easy, right? Plus negative 5 over x minus 2 squared. Is that natural log? Is that natural log? No, it's power rule, right? What's your first attempt going to be? X minus 2 to the negative 1, right? So this is power rule. This is not natural log. It's squared in the denominator. So it's not the natural log of x minus 2 squared, right? Natural log is for that one case where your denominator is to the first power. If you have any other power, it's power rule, right? Okay, and then plus negative 9 over x minus 2. Is it natural log?
Yes.
Yes. Quick. 10 times natural log x minus 3 plus, I'm going to have x minus 2 to the negative 1. The negative will take care of that negative. I need a 5. Plus negative 9 natural log absolute value x minus 2 plus c. Remember, check your answers by taking the derivative. You need to get the exact same thing you started with. If you're not sure, take the derivative. But you got to know how to take the derivative and do that right. Questions on this one? Okay, so there's an issue I haven't brought up yet, and that's the issue of how do we choose what kind of thing is up here. So far, everything in our numerator says end up being constants. And that's why I just put like a capital A, capital B, capital C. What that represents is just a constant number, a value. So if we have more complicated factors that are of higher power, so this is actually power 1, and this is still power 1 because it's x minus 2 squared, but it's still considered power 1 because of the x minus 2, and this is x minus 2. So we consider all those things in the denominator are power 1. And so if you take one less than power 1, you get a constant. And that's why I chose constants for all these things. So what goes in the top, these unknown numerators, are always of power 1 less than your denominator. 1 less than your denominator. All these are considered power 1. X minus 3, x minus 2, x minus 2. Because those are all considered first power, we take 1 less, which is 0 power or constant, and that's what I put up here, constants. Constant, constant, constant. So let's look at an example where we have to do something different. Questions on this one? So here, is degree of numerator less than degree of denominator? Certainly. Degree of numerator is 0, degree of denominator is cubed. Does the denominator factor? Remember, these are the two things that have to be true for partial fractions. Yes. How does it factor? X times x squared plus 4. There's our common denominator, so we're going to have something over x plus something over, does x squared plus 4 factor down anymore? No, x squared minus 4 does, but not x squared plus 4. That's the simplest you're going to make that. You can't factor that anymore. So, power of x is 1. 1 less than 1 is constant. Now this one is a non-factorable quadratic. I can't split this apart anymore. So this truly has power 2. It's quadratic. 1 less than that is 1. So I need a linear term up here, which means bx plus c. So what the unknown thing in the numerator is always a polynomial of 1 degree less than your denominator. This is the first time we've actually seen something other than linear in the denominator. So it's quadratic, so now we're going to make the numerator linear. Caden?
If we, like here you can't simplify x squared plus 1, you can't factor it out more.
Right.
If we have x squared minus 4 and we factor it into the third term, would it still work?
Yes, you have to.
You have to factor it
So you'd have x, and x squared minus 4 factors to x minus 2, x plus 2. And you'd have to keep factoring it all the way.
Okay. So
And then this would be all linear terms.
okay.
This would be all linear terms. A, B, C. Other questions? Okay, now everything else is the same. Now that we got the numerators correct, we got this bx plus c, everything else is the same. So we're going to have a times what? X squared plus 4. For the numerator over here. And bx plus c times what? We need another x, right? Top and bottom. I need to multiply this by x squared plus 4 over x squared plus 4. That gives me this in the numerator. I need to multiply this one by x over x. That gives me bx plus c plus x. Equals? All right, how many x squares does it equal? How many x's? And how many constant? So we're going to have ax squared. Everything else is the same now. A times 4, 4a. Bx squared, cx. X squared terms. A plus b. Linear terms. 4a. Nope, C. Constant term. So this one's easy to solve. A plus b equals 0. C equals 0. And 4 equals 10. So we get that. A equals 5 halves. B equals negative 5 halves. And you're off to the races. Okay, this one, just let me give you a heads up on this one. So the 5 halves over x, that's easy. This one, how do we take care of negative 5 halves x plus 0? So just make, okay. Over x squared plus 4. How do we do it? Who has learned something?
Isn't that just
Undoing the chain rule, right? You got the right powers here. X to the first in the top, x squared in the denominators. First attempt is, so this is x squared plus 4 to the first in the denominator. Natural log x squared plus 4 is the first attempt. Take the derivative, clean up the mess. Have a good weekend. Web work, yeah, web work for Monday. Web work.